This is part 4, RNN, of the series AI for Everyone. We will only look at two of neural networks, RNN and CNN, which revolutionized the AI field, as they could be used commercially across industries. Let's first explore RNNs and learn where they can be used and what limitations they had. Recurrent neural networks, RNNs, are named for their ability to recur by feeding the output of a previous time step back into the network as input for the next step. This feedback loop allows RNNs to maintain a form of memory, making them well-suited for sequential data processing tasks, such as time series analysis and natural language processing, NLP. In contrast, feed-forward neural networks process all inputs simultaneously, without any mechanism to retain past information. RNNs, however, process inputs sequentially, maintaining an internal state that captures past information across time steps. At each step, the network updates its hidden state, which is then passed to the next step, allowing the model to retain context and recognize dependencies in sequential data. This ability makes RNNs particularly effective in modeling time-dependent patterns and understanding contextual relationships in data. RNNs are useful for tasks that require understanding the context or order of the input data. They can be used in language modeling and generating text, where it can learn the structure and patterns of natural language and generate coherent sentences or paragraphs based on a given topic or prompt. RNNs can also be used in translations, where it can encode the meaning of a sentence in one language and decode it into another language, preserving the grammar and semantics. RNNs can also be used in speech recognition, where it can convert spoken words into text by analyzing the acoustic features and temporal dependencies of the speech signal. RNNs can also be used in generating image description, where it can produce captions for images by combining the visual information from a convolutional neural network, CNN, with the linguistic information. RNNs can also be used for video tagging, where it can recognize the actions or events in a video by processing the frames as a sequence and learning the temporal dynamics. RNNs can also be used to summarize paragraphs, where it can extract the main points or keywords from a long document and generate a concise summary. RNNs can also be used in time series prediction, where it can model the trends and patterns in time series data, such as stock prices, weather, or sensor readings, and forecast future values. RNNs can also be used for natural language processing, or NLP, where it can do text mining and sentiment analysis. It can analyze the meaning and sentiment of text by capturing the syntactic and semantic relationships between words. RNNs can also be used for named entity recognition, where it can identify and classify the names of person, organization, location in a text. Of-course, quality of recognition will depend on what it has been trained on. So you may wonder if it could be useful in so many scenarios. Why was it not so popular or widespread like LLMs of today? RNNs had many problems, like vanishing gradient problem. What this means is, if the sentence is very long, it forgets what is at the beginning of the sentence, as it can only remember the most recent words. This is kind of a memory problem. Exploding gradient problem. This occurs due to the mathematical process it uses in backpropagation, where gradient becomes too large. It's like a snowball rolling down the hill, and it grows bigger and bigger as it reaches downhill. Here, gradient is the value that determines by how much a weight should be updated during training. The gradient is simply the derivative of the loss function with respect to a weight. Also, training an RNN is a very slow process, as it can only process the information in sequence. These limitations have led to the development of more advanced RNN architectures, such as long short-term memory, LSTM, and gated recurrent unit, GRU, which are designed to address some of these issues. While LSTMs and GRUs solve some problems, they still face several limitations, like one, sequential nature. Both LSTMs and GRUs process input data sequentially. This dependency on previous computations limits parallelization, making training slower on large datasets. 2. Scalability issues. Training LSTMs, GRUs on very large datasets or very long sequences becomes inefficient and computationally expensive. 3. Fixed size context window. Despite improvements, LSTMs and GRUs still struggle to capture dependencies over very long sequences. Their memory is inherently constrained by the size of the hidden state. Bidirectional LSTM by LSTM is very popular RNN, which is an extension of LSTM RNN that processes information in both directions. It is used by Google Assistant, Siri, and Amazon Alexa for NLP tasks, and they can run on high-end mobile chips. It has anywhere between 1 to 6 layers of neurons and neuron per layer, anywhere between 128 to 2048. Now, RNN has been replaced by transformer-based architecture like ChatGPT,